Hello friends, how are you all today? Have you ever wondered what operating system is and how it is going to work? It's coming up right now. I'm Prashant, a technical trainer and freelancer from Dharani Academy of Technical Education, Bengaluru. Let's start with the concepts of operating systems. So we were discussing about the swap space, right? And swap space is being executed in such a way that, right, whenever a particular variable is missing, it has to be replaced, right? All right. So now let's consider an example. Okay, let's look at an example how this is going to be handled by using this. Okay, now let's say the page fault occurs during an instruction fetch. Let's assume that there is an instruction which is being executed. You are executing some instruction and there is a page fault. Okay, so let the page fault occurs during the instruction fetch. Okay, so we know that whenever computer executes an instruction, the execution overall has three different phases. First one is to fetch, second is decode, and third phase is execute. Right? Execution is if you have some operation, the carrying out of that operation and storing the result. Right? So first you fetch, you understand what instruction it is, that is a decode. Then required variables needs to be fetched, right? Perform the operation, store the result. Okay, let us say during an instruction, whenever the instruction fetch, there is a fault, right? So what is the suggestion now? If this happens, right, we have to restart the fetching of the instruction once again, right? So restart the instruction by fetching it again. You need to do this is absolutely necessary. Okay, if a page fault occurs while fetching an operand, right? So you see there are two types of fetches. I'll come to the example immediately, but for the time being let's write the second statement, right? This is page fault occurs during the fetching of any operand, right? So if page fault occurs during the fetching of an operand, then what happens? We must fetch and decode the whole instruction once again, because, right, I fetched the instruction, I understood what I have to do by decoding it. When I decoded the instruction, I understood that okay, I need these variables, say variable a, variable b, etc. A variable a is available, but when I try to read the variable b, there is an error. B is not present in the virtual memory, so you have a problem, right? You go through all the 6 steps we discussed yesterday, you come back, now b is available, but you cannot continue from there. You have to fetch. Why you needed b, you don't know, right? You will go back, you fetch, you decode, then you come back and fetch once again a, fetch b, then you proceed. This is how it's going to work. Okay, so if the error occurs during the fetching of an instruction, no problem, you don't waste a lot of time. But if you do, if there is an error occurring during the fetching of an operand, then whole process needs to be repeated. Okay, so if a page fault occurs during the fetching of an operand, uh, I can say we must fetch we must fetch and decode the instruction again. Okay, and then fetch the operand or operands, because most of the time we have multiple operands. So let's consider an example of this scenario by, so let's say that we, right, have a three address instruction. Okay, example, three address instruction. So let's write the instruction add is my instruction, a comma b comma c. So what is our intention? Our intention is c is equal to a plus b. This is what we want to perform. Take a, take b, add them and put it into the destination dc. Okay, so what are the steps to execute this instruction? Are, first one is fetch the instruction. All right. Sorry. The second step is you try to understand what is the meaning of add a comma b comma c, because what we have written, what we are writing over there is not the binary language. What we are writing is assembly is not understood by the machine, so machine should decode that. So the second step is to decode the add instruction. It understands what it has to do when the instruction is add. Okay, now step number 3, right? It understands, okay, this is a 3 byte instruction. There are 3 memory locations associated with this instruction, that is a, b and c, out of which a and b are the source from where I need to fetch 2 operands, and c is the third operand, which is the destination. Okay, so you will fetch one by one. Now you see, this is the fetching of the variable. So fetch a. So the fourth step should be fetch b. Step number 5 should be perform addition, add a to b. Okay, once that is done, in the step number 6 you store. All right, store the sum to c. Okay, now you see that in this particular example, we get variety of examples possible in the reading and writing operations related to the memory of a computer. All right, but you can check that in this case fetch a and fetch b are basically, they depend upon the virtual memory, because if a and b are present in the virtual, you can read it easily. Okay, but let's say that there is a fault when we try to store result in c. Okay, can you guess why? It's because c is a page not currently in the memory, because c is a destination, right? It's a physical location on your hard disk, right? So when you want to store this in store the result in c, and right, c is not a page, so there will be a fault if you try to write something onto that. So we have to get the desired page, bring it in, correct the page table, and then restart the instruction. So if at all the machine tries to access the c and there is a fault, normally there should not be a fault, because c is something like the destination which is present in the hard disk. So page table will definitely say that it is not present in the uh, it's not loaded to the main memory. So we'll write that point. So if at all there is an error during these phases, we know that you need to completely restart the instruction. Okay, but if at all C is not present, so that means if fault occurs when uh, storing the result to C. Okay, we have to get the desired page, in a sense load it to the memory. Okay, loading is called as a bring it in, and when it is when it is present in the memory, you need to update the table. Okay, comma, uh, update the page table. These are the steps needs to be done. Now the restart will require fetching the instruction again, decoding again, fetching the operands, and then adding them, and then storing the result. So when, what do you mean by restarting of an instruction, right? This is the procedure corresponding to this given example. Okay, but okay, this is common. This is normally computers will handle these issues very easily. Okay, but what happens, let's look at the same issue in a different way, where we can see the major difficulty. Okay, uh, that is when one instruction may modify several different locations. Okay, so that's the major issue. So for example, you try to move characters, right, for several locations, one complete block, right? Page fault might occur after you move partial data, like you are copying say 10 MB file. Okay, you're passing a 10 MB file from one location to other location. There is a fault that is actually occurring right after some time, right? So I'll just try to explain what exactly is going to happen now. This is a one simple problem. We try to solve it now. You simply have to restart. But let's discuss about the bigger difficulty. Okay, a major difficulty arises whenever whenever an instruction modifies several locations in the memory. Okay, so for example, this is the case. Maybe you have a memory location starting from 0, 1, 2, 3, 4. Okay, and corresponding to these addresses, you have certain data stored in the memory, right? So, and I have another memory location, maybe starting from 55, 56, 57, 58, 59. So these are the addresses corresponding to this. Let's say it's empty. All right. As of now, I don't have it. So there is an instruction which copies the which not copies, which moves, because the example is we don't see the problem when we copy. We see the problem when we move it. Okay, when you cut and paste, right? So that means right, you are loading some numbers and you are moving one by one, right? You are moving one by one basically refers I actually moved this to this. Some number you may have, okay, or some characters you may have. Let's say the characters are A, B, C, D, and E. So I moved A here. Now you see that A is not there. I moved A. A is not there. Similarly, B and C I moved. Okay, so the content has been moved from location number 1 to location number 56, which is B. Similarly, this is moved to this location, so C. But now you see that there is an error saying that the page fault occurs here, saying that B does not exist. B is not there, right? Okay, so we cannot move. This move is not possible. So there is a page fault occurring. So this means there is a serious issue now. If you stop this execution, you go back and make sure that D will come into the memory from the hard disk, and then you try to execute this once again. You restart, correct? As per the previous step, we understood that we need to restart. But when you restart, now you see that there is no A here, there is no B here, there is no C here. It's already been moved, right? So that's the problem now, right? So whenever you are trying to modify, so that's what is the meaning of this sentence. Any instruction which modifies several locations, you can see that 5 different locations are being modified, so because of which you have a serious problem coming up. Right now we need to solve this issue. So first let's write about the issue that we are going to face when I try to modify several locations. Okay, so that is, so okay, we write while moving several blocks of data from a source to the destination, from one source to another part, that is a destination, right? A page fault may occur. There may be a page fault occur. All the old values are written back into the memory before the trap occurs, right? If there is a page fault, this is how it's. So this entire action restores the memory to the state before the instruction was started, so that the instruction can be repeated. So your idea is that, right? I'm coming to the solution part later, right? We have the problem which causes the trap here. Okay, a page fault may occur. So why we know that, right? One of the data in the source is not available. So because, right, when I try to restart, I don't have the data present in the source. So what is the solution? We'll try to have a solution in several possible ways. So we use temporary registers. So to solve this issue, we use the temp referring to the temporary registers. Okay, registers to hold the values of overwritten locations. The values of the overwritten locations, whichever location are being overwritten, right? We are trying to hold those values. In the sense, you don't copy a directly to the destination. Your a will be copied and saved in the temporary. B is also going to be until and it's going to check that whether there is a page fault occurring, or will there be a trap. Okay, if the trap is detected, immediately these values which are copied will be put back into the original location so that you can restart. Okay, so that's the idea here. So if there is a page fault, if there is a page fault, all the old values, each and every old value, right, are they are returned back, okay, to the memory, to its state before the instruction was started. Okay, so that instruction can be restarted. So this means, this implies what, right? You can restart. Restart is possible. This is one of the solution which most of the OS will follow. There is another solution to this. uh, there will be a micro code there. The other solution, this is the first solution which is easiest. There is another solution, I'll write another solution we have, where you write a separate code. We call it as a micro code that computes and attempts to access both ends of the blocks, right? Both ends of the blocks are referring to, you are trying to access 0 and 55, and the other address, sorry, that is 4 and 59. On both sides you try to access the source as well as the destination. Okay, both source and destinations are going to be checked by using a microcode, right? If page fault is going to occur, right, in this step, before anything is modified, you will come to know that, okay, there is a page fault. But you don't execute anything, right? You are not actually executing anything in that case. You are simply checking whether there is a page fault. So to check the page fault, you can write a separate code that is called as a microcode, right? uh, so the other solution is a microcode can be used to access the source and destination, okay, to access the source and destination, to check for page faults beforehand. So initially you check that, then if nothing, no problem, you can proceed. This is the other option, but you need to write a separate code. You just have to keep executing this code, right, every time. So both the techniques have their own advantages and disadvantages. Okay, all right. Now let's go ahead. There is, let's look at the demand paging concept, its performance. How do you measure the performance related to a demand paging? So that is next side heading, its performance. So now we know that we modified the concept of memory by using a virtual memory. Virtual memory requires demand paging concept. Whichever is needed, I load. Okay, now I just have to make a comparison saying that, what if I don't use a virtual memory and I try to execute the code normally? Okay, let's say I measure something, I should compare the same thing by using the virtual memory and executing the same thing, so that you will come to know that uh, whether the demand paging is going to help us or not. All right, so for that reason, we have what is called as, right, the performance of the demand paging can be measured by using what is called as the effective access time. So this is the performance measurement that we use to identify, right, the effective access time. All right, so normally the normal memory access time, right, we have something called as right, the time required to access the computer's memory in a very normal case, right? There is no virtual memory. Every instruction has some operands that needs to be fetched directly from the hard disk. Okay, it's not present in the virtual part. In that case, whatever is the time required, we call that time as memory access time. All right, so we'll first define what we need. So let there is a term called MA, right? This be the memory access time of a computer, right? So normal range could be, right, something around 20 to 200 nanoseconds. This is the range for any general computer. There are faster computers as well, but in general, okay. Now, if at all there is no page fault, right, then you see that the effective access time will be equal to this itself, because there is no fault, right? Whenever you read a variable, say a, if it is not present, it will be coming from the memory, right? So that's what. But the page fault occurs means we have some changes coming up. Okay, if at all there is a page fault occurs, right, we have to read the relevant page from the disk and then access the desired word, right? If so, will make two things very clear here. So if no page fault, this implies the effective access time is equal to the MA, memory access time, right? But if page fault occurs, then it changes. So if the occurs, right, now we know that there is a difference. So what is the difference? We need, what are the steps we need to carry first? So we must uh, read the relevant page, okay, uh, first. From where? From the disk. This has to be done first. You read it and then you access the desired data or desired word. That's fine. This is how it works. So in order to calculate this part, the additional part, we will use what is called as a probability concept. In the sense, let's define something more now. So let the small letter p, right, be the probability of a page fault, because you see page fault will never occur regularly. Okay, it's a random thing, right? By chance one of the variable is missing, there is a chance, Okay, so because of that, we are defining what is called as the probability. Let P be the probability of page fault. So we know something about probability. This is always 0 less than or equal to p less than or equal to 1. But if you say it is close to 1, it is a definite event. Definite event indicates that, right? Okay, most of the time this occurs. If you say p is close to 1, it's a definite event. It is 1 means definite. If it comes closer, you can say that it's right. It's a regular event, but it's not regular. I said it's an occasional case. So what happens, right? So since the page faults are occasional, this implies, right, p will be closer to 0, approximately equal to 0. I'm not saying it is 0. 0 means it will never occur, but it's not that. It's close to 0, right? So now this is how the calculation happens when we use these concepts to calculate effective time. So therefore, the effective access time, this is equal to the 1 minus this probability into this times MA, memory access time, because that is a normally occurring thing. Memory access will be there 1 minus p times, plus the p times, p is the probability, into whenever this p occurs you have a page fault, so we call it as a page fault time. So this is the equation, right? So what is this page fault time, right? Page fault time, right? In order to, whenever the page fault occurs, whenever the trap occurs, how much time is needed to solve that, right? So how much time is required to service that page fault is what is called as the page fault time. Others we know now, right? Let's discuss about the page fault time. Okay, so here the page fault time is the required to resolve a page fault. Depends on type of the page fault, right? Again, we, in order to calculate this particular value, right, there is a sequence of steps, right, to be followed. In a sense, whenever there is a page fault, it causes the set of sequences, okay, to occur. So we'll write that. So in general, the page fault, okay, I can write causes. In general, a page fault causes the following sequence, right? So what are the sequence? We'll write one by one. So we know that as soon as, right, something is missing from the memory, it is not there, right? First step itself is generating a trap. Okay, this is trap to the operating system. Step number one, right? As soon as this happens, we know that save your registers and state of the process. Okay, so that is, so see, everything will require some time. So the total page fault time will be the sum of everything. Okay, so save the registers, and you also save the state of the process. So yesterday we saw several other things which you need to save, right? We understand that. Okay, everything will save. So second time is related to this. Then the third one is actually you are supposed to determine that the interrupt was a page fault, because normally whenever something happens there is an interrupt that is occurring inside the right software. Interrupt will occur. So types of interrupts are there, right? So the controller needs to identify what type of interrupt it is, and from the types of interrupts possible you need to detect that okay, this interrupt is because of a page fault. So it takes some time for that. Okay, so that is determine that the the interrupt was due to a page fault. Right, as soon as interrupt occurs you will need to identify that yes, this is because of a page fault. Then step number 4, in this case check that the page reference was legal and determine the location of the page on the disk. It takes some time to do that. So this is the next step that's happening. So you will check uh, the page reference. The page reference was legal. Okay, and you also have to determine, right, where is the page on the disk. It's like you have a copy of that data, right? So you need to identify, determine the exact location of the page on the disk. Right, now once it is located I need some more time for the next step, which is step number 5. So I have to issue a read from the disk to free frame, because we know that yesterday we saw that there will be what is called as a free frame. We need to read something. So that means you issue uh, a read from disk to free frame. Right, this actually can have several other parts, like you may have to wait in a queue for this device until the read request is serviced, because you see that whenever you request a read, so CPU says that I want to read something, right? That request will wait in a queue if there is something else which is being executed during this time, because yesterday we saw that whenever there is an interrupt that has been requested, interrupt that has been arised, before servicing you will store something, right? During that time the control can be given to any other process which is waiting, right? If that is happening, now you issue a read signal, right? You may have to wait because something else is going on, right? So that's what is the first part. The second thing is that if at all the disk which you want to read is busy, because somebody else is accessing that disk, means you have to wait so that the disk becomes available. So nowadays computers will have 4 or 5 disks maybe, right? Some high end hardware device will have multiple disks. In that case there is a possibility that one of the disk which you want to access is not available, in the sense it's busy, or there could be some latency issues related to the disk. So though you say that though you issue a command saying that okay, I want to read this particular disk and even the disk is free, disk takes some time to respond to your signal. It is called as a latency, right? There can be a waiting time for that. Okay, and then the transfer will also take some time, transferring the data from disk to your whatever free frame it is, right? It will take some time. So normally you have 3 different times here, right? I'll just write in a bracket just for our reference. So this particular fifth step will normally have multiple things which is in. So you can have a waiting in read queue. This could be the first thing, that is plus, right? Wait for the disk, uh, seek, or there can be a latency. This is what I told about. The disk may take some time. Plus the uh, data transfer from where to where? From uh, the disk to the free frame. Okay, this is the fifth one. Then let's go to the next step, step number 6. So see that the step number 6. Now during all this time, anyway, CPU is idle. So CPU should not be idle for any reason, because it is, you are wasting your energy, your time, etc. So what you do, right? You will allocate the CPU for some other user. Okay. So when that happens, once this reading has been completed, you may have to wait back so that CPU becomes free. Okay. So we can write that. Uh, we can write, okay, while waiting, allocate CPU for other users. Here users are the processors. Okay, give it to anybody, some others was waiting, right? Maybe this is the case. There is another option here, right? That is, you allocated the CPU to someone else, but that someone else is a IO device, right? So normally we know that IO will take more time than the simple CPU time. So, right, whenever CPU is executing something else, there is an interrupt from IO. So what CPU will do, CPU will give a preference to that particular interrupt, right? So that time could be, we are writing all possibilities, everything might not happen. Okay, interrupt from uh, the IO, input output device, until the IO request is completed, right? CPU will not come back. So you have to wait. So the time corresponding to that also have to be, right, checked here, right? Then save the registers and process the state for the other user, because you are coming back means if you want to go back, you may have to save that. So there may be a time related to that. Okay, so eighth one is save registers and the state of processors. Sorry, not processor, processes. Mistake. I'll just write a process. Okay, of other user. So the same user which we discussed here, this is the same. Okay, that users, right, things you need to save, because interrupt came, you save it, right? So once again, what type of interrupt was arise, you need to identify, correct the page table, right? Go to a new memory, wait for a CPU to be allocated again, and restore your registers, process, page table. Then you resume the instruction. Okay, so so many steps are left over. So this is step number 9, is identify, determine the type of interrupt. It will take some time. So because of that, you may have to update the page table, right? So then we'll go for the 11th one, right? Wait for the CPU being scheduled, because you know that already you are servicing something else. Your particular instruction is in queue now. So you have to wait for the CPU getting allocated to this particular process which is waiting. So we call it as wait for CPU scheduling, right? It will get first priority, second priority, or some priority. According to that, it will be allocated the CPU. So wait until then, right? Once it is allocated, right, then you come back and do the restoration, restore the registers uh, status, and once again you may have to update the page table to resume the instruction. So you see that totally this much time is what has to be uh, considered when you calculate the time that is called as page fault time. Okay, all right. Now let's say, so here we are writing all the steps that might be used. Okay, this is the worst case. Worst case is all the 12 steps might be arrested. But if you see, right, let's say that there is no what you call IO interrupt will not occur means, right? Every step that is corresponding to the IO interrupt, you can simply eliminate, because that's not happening in this case, and you can, so in that case the time is less. But if why we wrote all the 12 steps, because this is the worst case. Worst case could contain all these numbers. Are you okay? Okay, now let's let's do a let's solve a simple problem. Okay, simple problem based on the equation which we wrote above. Okay, if the average page fault service time is 7.98 milliseconds for a particular computer hardware with the standard memory access time approximately 185 nanoseconds. If the if page fault occurs 3% of the time, then calculate the effective access time of the system. All right, so we can see right? The smallest time is in the nanosecond, so we are expecting the answer in the nanoseconds. Okay, uh, two values have been given, one in milliseconds, one in nanoseconds, right? So we will calculate using the same equation, that is, so I just write a short form, effective access time. Let's write EAT. Okay, EAT is equal to 1 minus P into MA, correct? uh, Plus, I think, P into uh, the page fault time. Okay, I can write PFT. These are the two times which we need to substitute. Okay, so what is 1 minus P? So you see that the P is 3%. It's a probability, so you need to write it as 0.03. 3%, so 3 by 100. Its probability of occurring is this. So this is 1 minus 0.03 times the access time. So we'll write in nanoseconds. So that is into 185 into 10 to the minus 9. Okay, substitute for nano. Nano is 10 to the minus 9 plus, right, the probability, that is 0.03 into, you can check that, what was the value given, 7.98 milliseconds. Okay, so this is 7.98 milli means 10 to the minus. Okay, so you have to give an answer, right, into 10 to the minus 9 outside. Keep that 10 to the minus outside. Simply you can enter this whole thing in the calculator, get the answer, and convert that into 10 to the minus 9. You move it out, remaining you can give the answer. Okay, so that comes in nanoseconds in total. So the answer comes to be equal to 2395794.5 nanoseconds. So always the standard way of representation is that whichever is the smaller time unit, you present your answer in that, using that particular mode. Nanosecond is the smallest, means you have to give the answer in the nano. If at all you had microseconds and the milliseconds, we are expecting the answer in the microseconds because micro is smaller. All right, so that's the concept everybody should follow, right, when you try to give an answer, okay, in engineering. That's all for today. Let's resume the concepts in the upcoming classes. If you have any doubts related to the topics we discussed, please feel free to contact me anytime. Thanks for watching. Have a nice day. Goodbye.